In this video, I'm going to explain about one more technique used to solve critical section problem, that is semaphores. Okay. In my previous video, already explained about one simple software solution, that is Peterson solution. Okay. What is the advantage of Peterson solution? It is very simple. It is a software solution, no need of any hardware instructions. Okay, but the disadvantage is it can be applied only when there are two processes are in the race. That means when only there are two processes wants to enter into the critical section, but we need to allow any one. Okay, at that time, if more than two processes are in the race to enter into the critical section, then it is not possible to apply Peterson. So to overcome that disadvantage, we discussed hardware solution. So that is two methods. That means that hardware solution uses some machine instructions, and those machine instructions should be in atomic instructions. That means non-interruptible. That means that is test and set and swap. That means when those machine instructions are executing, interrupts are disabled by our operating system. So interrupts are not allowed when that atomic operations are executing. Hence they are called non-interruptible instructions. Okay, that's what the machine instructions. So now we are discussing one more method called semaphores. Okay, again it is a simple software solution, but it is not that much complicated when compared to other two. Okay, see, always hardware solutions are complicated to implement, whereas this semaphore is a very simple when compared to the two previous. Okay, and we know that in every program, so we have some part of the program they are not shareable, and there are some part of the code that is shared, and that is what we call as a critical section. Some part of the program which is shared, so that we call the critical section. So that critical section should be accessed only by any one process at a time. So generally any cooperative process structure is this one. Okay, any process. Okay, any process, this is the structure. So we have any process wants to enter into the critical section. First they have to check in the entry section, and then if it is critical section is free, it should be allowed. After doing the critical section, then it has to come out exit section, indicating that I am coming out of the critical section, and then the remainder section. So this we discussed in the previous videos. Okay, now we know how entry section is implemented in Peterson solution using two variables called flag and as well as a turn. Okay, and we know how to implement this entry section using the lock. Okay, in the case of test and set and as well as swap. Okay, now we will discuss how semaphores are used to solve this problem. Okay, now what these semaphores are basically, these semaphores are basically just an integer variable. That's it. How we are using, say, int a comma b or int x comma y, like that. These semaphores are just an integer variables. But this is not an ordinary integer variable. These are all what? These are the integer variables. Okay. Now I will call the name yes. Okay, yes. Because semaphores I will give the name yes. Somebody use the word mutex. Okay, mutex. Okay, that means either you call yes or mutex, or you can give any name by your own name also. But basically these are what? They are some integer variables. But the condition is these variables should be accessed by two atomic operations. Atomic operation, one is wait and another one is signal. Okay, so these are the semaphores are nothing but integer variables that can be accessed only by two atomic operations. Again, atomic means non-interruptible, and those atomic operations are wait and signal. That means this function only should access these semaphores. Nobody else, that is no other instruction can access this semaphores. Okay, so that's what a special variable we call as semaphore variables. Okay, semaphore is just like integer variable, but it is not an ordinary not an ordinary integer variable. It is a special type of integer variable because semaphore is just a variable, and these variable can be accessed by two atomic operations, wait and signal. What this wait will do? This wait will just decrement the semaphore value. Okay, it doesn't do anything. Wait will just decrement the semaphore value. Whatever the semaphore variable, it may be yes, it may be mutex, it may be x, whatever, you just decrement the semaphore value. Whereas signal, what will do? Signal will do opposite, increment the semaphore value. That's it. So one will decrement, another will increment. That's it will do. Okay, it's very simple. Now, how to define? Now, okay, how to define wait? So now wait is defined as wait of yes. Okay, now I will say while this yes is less than or equal to 0, do nothing, and then do yes minus minus. That's it. This is my what? Wait function, atomic operation. Wait, what we do? Check the value of s. If it is less than or equal to 0, comes out. Okay, we know the wait condition. In general, this is the general syntax of what? While loop. So while condition is true, if the condition is true, what happen? First check the condition. So if I execute here, check the condition. If the condition is true, comes inside the while loop, execute all the statements. After executing all the statements of the while loop, again it goes back to the condition. So again condition is checked, again condition is true, comes inside, execute all the statement, again go to the condition, again condition is true, comes inside, execute all the statement, like this, keep rotating. That's what the loop. Only control comes out of the while loop. Control comes out of the while loop only when condition is false. Same thing now, here I run this one. Okay, that means like this. That means check the condition, again check, okay, check, okay, first execute here, check the condition, condition is true, comes inside, but here nothing. I am doing nothing, do nothing. That means there is no statement within the while loop. So condition is true, comes inside, do nothing. Again, after that, go back to the condition. Again condition is checked, again condition is true, comes inside, do nothing. Again go line again. So now again here also, control comes out of the condition, out of the while loop only when the condition is false. This you can also be written like this also. Both are same. Whichever you feel easy, write like this. So similarly like this. Now wait of s, in that if the condition is true, comes inside, do nothing, go, it will be stuck here, condition is true. Then control comes to this s minus minus only when the condition is false. Okay, this is what wait and while. Now signal. Signal is very simple. Signal of s, just it increment the s value. That's it. These are the two atomic operations. Only these two operations, these two functions can use the semaphores. Nobody else can use the semaphores. That's what the semaphore. Now, these semaphores may be binary semaphore or counting semaphore. There are two types of semaphores. Okay, it may be what? Binary semaphore, or it may be what? Counting semaphore. These binary semaphores also called as mutex. Okay, these binary semaphores also called as mutex. Okay, and counting semaphores. Now let us discuss binary semaphores. How binary semaphores work. Okay, now again coming back to the same thing. Now how intersection, exit section, how it will be implemented. That is the only thing among these all the methods. Now, okay, now again summary. A semaphore is a technique, or we can say tool or a method used to avoid critical section problem, or it is used to make coordination between the processes which wants to enter into the critical section. By coordinating among multiple processes, it will allow any one process to enter into the critical section. That's what the semaphore, and is an integer variable. It can be accessed only by two atomic operations, wait and signal. Wait decrement, signal increments. Okay. Now let us say two processes are in the race to enter into the critical section. So now process P1 wants to enter into the critical section. Process P1 and assume process P2. Now for both are using this common shared variable semaphores. Okay. So now for P1 I will write do. Okay. Now I will say weight of yes. Okay. That's it. Weight of yes. Then signal of yes. Now here in between I am having what? Critical section. Okay, then I am having what? Reminder section. This is process P1. Now similarly same process P2. Now this is critical section. Again, the remainder section of this process. Okay, remainder section only changes from one process to another process because this is independent, not shared. This is shared, so common. Now I'm having only one critical section, and with the one critical section, P1 also wants to enter, P2 also wants to enter. Now I check with only one. Okay, now initially my semaphore yes variable is initially what? 1, indicating what? Our critical section is free. No one is there here. No one is in the critical section. See, again I'm telling, this is not two different critical sections. There's same shared variable, same shared data, same shared resource, whatever. This is same. Now assume P1 wants to enter. Now, whenever P1 wants to enter, first you check weight of s. Yes value, now it calls the function. Now control goes to here. Now weight of s. Now when control comes to here, it is a calling function. Now control goes to here. Now from here, control goes to here. Okay, now weight of s value 1, s value 1. Now 1 it comes inside while 1 less than or equal to 0, false. 1 is not less than or equal to 0. Condition false comes out of while loop, s minus minus. That means it will update s is equal to 0, decremented. Now it simply comes out. After executing all the statement, again control backs to the next statement. After the next statement, it enters. Now process P1 enters into the critical section. Now process P1 enters. Now assume process P1 is there in this. Okay. At this time, now assume P2 also wants to enter into critical section. Now again P2 comes here, weight of s. Okay. Now we check weight of s. Weight of s. Now again checks. Now s value is what? 0. Set zeros. Now this will receive 0. Now weight of s is 0 less than or equal to 0. True. Condition is true. Comes inside the while loop. Do nothing. Okay. When it comes to here, condition is true. Comes inside. Do nothing. Again goes to the while condition. 0 less than or equal to 0. True. Comes inside. Do nothing. It keeps stuck in the while loop. It never come to this one. Never coming out of this while loop. Because there the while loop means it is stuck here only. It is not allowed to enter into the critical section because already P1 is there in the critical section. So it will be avoided. Now, when P2 is allowed, whenever P1 comes out, assume it is keep stuck in the while loop here, keep stuck here only. So now that means this statement is used to block the critical section if somebody already is there in the critical section. Now it is blocked. Okay, now after some time, assume P1 completes its operation in the critical section. Now it wants to comes out. Once it comes out, now I go to what? Signal. Signal of s. Okay, s value is what? 0. It sends 0. Now control goes to what? Signal function. Now signal is 0. This is 0. Comes inside s plus plus. That means now s becomes what? 1. S becomes 1. After that, it comes out of the signal and it is in the reminder section. While it is executing in the reminder section, now assume now again, now this wants to, again P2 is keep checking along. P2 is stuck in the while loop. It is checking. Now again check. Yes is less than 0. Yes is becomes 1. 1 less than 0. False. Now control comes out of this. Now S becomes decremented. Now it blocks. S becomes 0. Now P2 enters into the critical section. Okay, now P2 is entered into the critical section. Now P2 is entered. Okay, now assume, now who is there in the critical section? Now P2 is there in the critical section. Okay, so now let us discuss. Now P2 is in the critical section. Okay, now P2 is there in the critical section. When P2 is there in the critical section, assume it is executed remainder section law. Assume it completes, again comes out. Assume after some time, again P1 wants to enter into the critical section. Again comes while true, again goes in, again weight of S value 0, 0 comes to here, yes 0, 0 less than or equal to 0, true, comes inside, do nothing, again now it P1 stuck here. Because why P1 stuck here? In the weight, that means P2 has blocked this. P2 is there in the critical section, means this weight blocked P1. So this is how this weight signal is used to block one process if it is already one process is there in the critical section. And simple words, if any one process in the critical section, other process is not allowed to enter into the critical section. So this is how, so here binary semaphores, here always the value of the semaphore is either 0 or 1. 0 or 1. We saw that. Okay. At any point of time, if we look into the variable, semaphore variable, this value is either 0 or 1. Hence it is called binary semaphores. Okay. Binary semaphores. Now let us discuss how to implement counting semaphores. Okay. Counting semaphores. Okay. Now let us discuss counting semaphore. Okay, so again in binary semaphore, always semaphore value is either 0 or 1. So that's what the binary, hence it's called binary semaphore. So simple analogy, example, assume I'm having one printer in my house. Okay, now since I'm having only one printer in my house, anyone in our family members, any one person can take a printout at the same time because only one printer. Assume two persons wants to take the printout. Now one person has to wait for another person to complete its job. So that's what we discussed. Now binary semaphores, we are having only one shared resource, that's one printer. Now assume now, see in our house, in house nobody will keep more than one printer, right? So that's why only one printer are there. So more than one person they have to wait until the first person completes. Okay, now assume you take one Xerox shop, okay, a printing shop, okay, so nearby your college or universities, okay, generally they are having minimum 2 to 3 printers, right? That is multiple printers are there because crowd will be more, so they are having multiple printers. Assume in the same way, now I am having printer 1, printer 2, printer 3, okay, 3 printers are there. For example, assume in one shop there are 3 printers are there. Now at a time, how many persons can take a printout? Assume no one are there, assume shop is open and the first person comes. So now first person can use the printer 1. Now first person is printing in printer 1. Now second person also come, he has to wait, no need because another 2 machines are free. Okay, so now another 2 machines are free. The first person is using this one and now second person will come, he can use one more machine. Now still one more machine is free. So third person will come, that person can use this one. So now suppose fourth person comes. Fourth person, now that fourth person has to wait for any one printer to become free. Okay, so that means here the same resource is same printer. I'm having 3 instances. That means when we are having multiple instances of the shared resource, then we go for counting semaphores. Now we will discuss how counting semaphore will be used. Okay, so when we go for counting semaphore, if there is a multiple instances of the same shared resource are there, then we go for counting semaphores. Suppose if you are having only single instance of a particular resource, then we have to go for binary semaphore. Okay, so now there's a concept. Now, assume now in this case, I am having what? 3 instances of same resource. Assume now initially what I will do, my semaphore value is initially 3 because I am having 3 instances. Okay, in 3 instances. Okay, now initially all 3 are what? Free. So now I make CS equal to 3. That means there are 3 instances of my resources free. Semaphore variable value is 3. Now assume, see I have done same thing, I have done 3 times. do P1, P2, P3, P4. Assume 4 now. Assume 4 process in the race. Assume process P2 come first. No, see, always I'm taking P1. Now that's why I'm taking P2. You can take any one. Okay. Now we'll take, for example, P2 comes first. Okay. Now P2 comes first. Now it wants to enter into the critical section. It checks. It comes here. Weight of S. S value is what? 3. S value is equal to 3. Now comes here. 3 less than or equal to 0. False. Comes out of the while loop. S will get decremented. Now S becomes what? 2. After that, it comes out of the while loop. Now comes here. Now it enters in the critical section. That means now one person is using this what? Printer 1. That is what? P2. That means P2 is using one printer. Still, how many are free? 2. So that's all the semaphore value indicates. 2 are free. Now assume P2 is using the critical section. Okay. Now while P2 is using, assume P3 comes. Now P3 also wants to enter. Okay. Now when it comes, now it will check weight of S. S value are 2. Now S value is 2. 2 less than or equal to 0. False. Comes out of the while loop. S value will be decremented. Now 1. Now it comes out of this one. Now P3 also started using. That means now P3 using one printer. Okay. Now while it is using, assume now P4 comes now. P4 comes, still how many are free printers? 1 is free, that's all semaphore value. Now it will check weight of S. S value is 1, so now S value is 1 here. 1 less than or equal to 0. False, again comes out of the while loop. S will get decremented, 0. Now it will be get allowed into the critical section. See now at a time P2, P3, P4 all are using. So now see P2, P3, P4 are using one resources. Now all resources are free, so all resources are full, no process printer is free, so that's why semaphore value is 0 now. Okay, now semaphore is not free. Now assume all 3 are printing, now assume now P1 comes. Now P1 also wants to enter, it enters, weight S, S is value 0, S now receives what? S receives 0, 0 less than or equal to 0, now the condition becomes true. Now the condition becomes true. Now enters into this one, do nothing, it again goes to the condition. 0 less than or equal to 0, true, comes inside, do nothing, it will be rotating here only. Because all 3 are busy. Now it will be in the while loop only until unless any one of these printer will get free. Assume it is keep rotating here only, keep checking. Assume after some time, for example, P3 completes its job. Now P3 wants to come out. Once it does its jobs, it comes to the signal of S. Now S value, right now what is S value? 0. That 0 is passed here, 0 will get incremented. Now S value becomes 1. When S value becomes 1, it comes to the remainder section. Now it is in the remainder section. So now again, now it will keep checking along. Now check S value. S value is what? 1. 1 less than or equal to 0. False. Now it comes out of this while loop and it decrements. Now it decrements, S becomes what? 0. Decrements and then it comes to the what? P1. Now it comes to the critical section. Now it enters. Now that means instead of what is that? P3, now it is P1 is using this one now. Now again 3 are busy. So again no printer is free. So 0. Now assume it completes its job. After again remainder section, assume it check comes here. While 1 true, again goes, again wants to do. Okay, weight is S value 0, 0, again the condition true, so again this will be stuck. So that means this is now waiting for P3 is waiting for any one of P1, P2, P4 to release. Okay, this is how counting semaphore works. So that means when we are having multiple instances of the same shared resource, at that time we go for the counting semaphore, and initial value of the semaphore is how many number of instances of that resource is there. That is, initially I took 3 because I am having 3 instances. If you are having 5 instances, initially is 5. That means at a time 5 process can enter into the critical section. After that, the sixth one has to wait. So if we are having n number of instances, so we can allow n number of process at the same time. Next, more than if n plus 1 the process come, it has to wait for any one of the process, n process to release. Okay, so this is what counting semaphores are used. Okay, so now we discussed how critical section problem can be overcome by binary semaphore, which is also called as mutex, and counting semaphores. Okay, hope you people have understood the concept. If you have any questions, please send in the comments. Thank you. Thanks for watching.